Hello, my name is Garrett Andreessen. I am a computer engineering major at CSU, and I'm going to be talking about the principal component analysis and recursive feature elimination as feature selection techniques. So feature selection is the process of eliminating unnecessary or redundant features. We did an example in class about this where we graphed the importance of all of the features and how much they were contributing to the output, and we only used the top 5 or so features. So an example of a redundant feature in some data set might be the date or the month, as this is usually, as a lot of things don't depend on what time they're done at. And recursive feature selection has a lot of benefits, including reducing the amount of data that is required to train a model. And this has lots of benefits, such as speeding up training time. There's also the potential for creating better accuracy compared to when using only features that are contributing a lot to the output. So in order to test these feature selection techniques, some special data sets were used. The first one is the Gazette handwritten data set, and this is a subset of the MNIST and uses 4s and 9s that are really hard to tell apart from one another, and the goal is to classify these to the correct number. And this data has been modified for a feature selection challenge by multiplying important pixels together to create higher order features with a more complex representation of the data. And this process results in about 5,000 features with 2,500 that are irrelevant or redundant to the problem. And the second data set is the Arsine data set. And so the purpose of this data set is to distinguish between patients with ovarian or prostate cancer and healthy patients. And this has also been modified for a feature selection challenge in a similar way, resulting in 10,000 features for each image. So now I'm going to talk a little bit more in depth about the feature elimination techniques themselves. So the first one we have is principal component analysis, or PCA. So PCA is a technique that reduces the dimensionality of the data by standardizing the data to have a mean of 0 and a variance of 1. So it then constructs a covariance matrix between all pairs of variables, and from this the eigenvalues can be extracted and ranked. And the higher the ranking, the stronger the correlation with the output. So then a new feature space is created using the top k values, where k is a hyperparameter specified by the user. Now, recursive feature elimination does this slightly differently. It does this by iteratively removing the least important feature from the dataset until the desired number of features is achieved. And this is also going to give us a k value, or we have to give this a k value, and it will give us a feature space with that many values in there. And so for this problem, we are going to be varying the value of k using a different number of features to see how that will affect the accuracy. In order to test our feature elimination techniques, we use a linear support vector machine with a margin value of 1. And so this very simple classifier is used because the focus of the project is on the feature elimination techniques and not on the classifier itself, and therefore a simple classifier is used to help keep things consistent, simple, and independent. And to make things a little better comparison, we implement a majority classifier as well. And so this majority classifier will always guess whatever class has the most instances in it. So, for example, using the Gazette data set, if there's more 4s than 9s, it will always guess 4, no matter what. This is important because this is also independent of the number of features that are being used. And to test out different values of k, we are using powers of 2 until either the max number of features is reached or each data point has been used. So these are the results for the Gazette data set. They can be summarized in the graphs below. So the blue line is the majority classifier. So this is at 50% because there's even numbers of 9s and 4s in the data set. And the yellow line up here, this is going to be the accuracy when using all of the features. And so this graph on the left shows all 5,000 features, and the graph on the right shows a zoomed in version of this, up to 120 features. And so both PCA and RFE were able to achieve an accuracy at or above using all of the features. So PCA was able to do this at 32 features, and RFE was able to do this at 256 features. However, RFE had the highest accuracy overall using 1024 features, and this gave 98% accuracy. We also have the Arsine data set. So the majority classifier put us at 56%, and using all of the features was around 87%. And then PCA was able to achieve this accuracy of 87% using only 32 features, and RFE was able to achieve an accuracy of 75% using 16 features. And the reason for there being less data points compared to the Gazette dataset is due to the lack of available data, with only 200 instances after being split for testing and training. The most features that could be tested was 140. And so RFE could have done better later, like it did on the last data set, but due to the lack of data, this could not have been tested, unfortunately. So these results that we have found are very significant because of the large reduction in feature space. So using PCA, we only need 32 features, which saves 4,968 features. So we only need about 0.64% of the total. And using RFE, we only need about 5.12% to reach that same accuracy. And these graphs down here show the amount of time it takes to train. And so as you can see, when you get up to these large numbers with PCA, it's going to take a significant more amount of time to train. And so it's really important to get less features in there if we can. And you also see a similar trend with recursive feature elimination. And this 128 to 1024, that's a much more realistic number of features to have. And looking at the Arsine data set, we save a lot more features, even more than in the Gazette data set. And the graph here does not show a lot because it only has to go up to 140 features, and so these all take a very small amount of time because of the very simple classifier. So overall, data will often have many features, but not all of them are relevant, and using these irrelevant features can lead to overfitting and poor model performance, and that is how PCA and RFE can improve your model performance by eliminating some of these redundant features. And using this classifier on these two data sets, PCA was able to outperform RFE in terms of how fast it was able to, in terms of the number of features it needed to reach the accuracy when using all of the features, and in terms of the amount of time that it took to run those as well, because PCA ended up being much faster. Okay, because this is a recording and not live, if you have any questions, you can email me. My email's on screen now. And these are my references that I used in order to make this presentation. Thank you very much for listening, and have a great day.